Hey everyone, and welcome back for another deep dive. We always try to cover the latest and greatest in astronomy and space exploration, and well, today we've got something really special for you. We're going to be talking about this incredible data set that's just come out of the Zwicky Transient Facility. That's ZTF for you in the know. And this data set is chock full of information about type Ia supernovae, and let me tell you, it's got scientists all abuzz, potentially rewriting cosmic history and all that jazz. So to get us started, just a quick refresher, type Ia supernovae, these are the incredibly bright explosions that happen when a white dwarf star, kind of reaches the end of its life and just can't take it anymore and goes kaboom. And the cool thing about these type Ia supernovae is that they're remarkably consistent in their brightness. And that makes them incredibly valuable to astronomers because we can use them as standard candles, like cosmic mile markers, to measure distances across the vast expanse of space. Now, these events are pretty rare. Think about it. We're talking one supernova per galaxy every few hundred years. So you can imagine why this ZTF dataset is causing such a stir. This thing has discovered a whopping 3,628 new type Io supernovae. And get this, it did it in just 2.5 years. We're talking about doubling the amount of data we've had from the past 30 years in just a fraction of the time. Absolutely mind-blowing.
It really is remarkable. The sheer volume of data that the ZTF is collecting is like suddenly having this high-resolution image where before we were squinting at a blurry picture. This level of precision is really a game changer. It's allowing us to ask and maybe even answer some seriously big questions about the universe that we could only dream of tackling before.
So we've got all this amazing new data. What's the big deal? What are we learning that we didn't know before? Give us the juicy stuff.
Okay, so buckle up. One of the most fascinating and maybe even a little bit unsettling findings is that type Ia supernovae might not be as consistent as we always thought. The CTF data suggests that the environment a supernova occurs in, especially its host galaxy, can actually influence its brightness.
Wait, hold on a second. If these cosmic mile markers aren't as reliable as we thought, doesn't that throw a wrench into all our calculations about the universe? I mean, how are we supposed to measure cosmic distances accurately if the brightness of these supernovae is all over the place?
That's the million-dollar question, isn't it? And believe me, it's causing quite a stir in the astrophysics community.
So what are the theories floating around out there? What could be causing this variation?
Well, one possibility is that there are factors we haven't fully accounted for, things that affect the brightness of these supernovae beyond just the properties of the white dwarf itself.
Like what? Give me an example.
Sure. We're seeing that supernovae in spiral galaxies tend to be a bit brighter than those in elliptical galaxies. Now, why that's happening, well, that's the big debate. It could be related to the chemical composition of the galaxies, the density of stars, or maybe even the presence of dark matter. It's all very much an active area of research.
So it's not just about the supernovae themselves, but about the entire neighborhood they're in. It's like they're whispering secrets about the nature of galaxies themselves. That's pretty mind-blowing. But if we're finding these inconsistencies in the brightness of type Ia supernovae, wouldn't that mean we have to reevaluate, decades of astronomical data? What kind of chaos would that cause in the scientific community?
Well, it's definitely a big deal. It means our correction mechanisms, the way we adjust our calculations to account for the distance and redshift of these supernovae, might need a serious overhaul.
And just remind us again how redshift helps us determine how far away these supernovae are.
Right, so redshift is this phenomenon where light from distant objects is stretched as the universe expands. The farther away an object is, the more its light is redshifted. And by analyzing the spectrum of light from a supernova, we can figure out its redshift, and from there we can calculate its distance.
Right. The farther away it is, the more its light has shifted towards the red end of the spectrum. So basically, this ZTF data is forcing us to question some pretty fundamental assumptions about the universe.
Absolutely. It's like shaking the foundations of the standard model of cosmology, that framework we use to understand the universe's history and evolution.
Okay, now this is where things get really interesting. So what are the alternatives out there? If the standard model isn't holding up, what other models are scientists considering?
Well, there are some physicists who are really intrigued by alternative models like modified Newtonian dynamics, or MOND for short. MO tries to explain the universe's expansion without needing dark energy at all, which is a pretty radical idea.
So we might actually be on the verge of a paradigm shift in our understanding of the universe. This VTF data really could rewrite the textbooks.
It certainly has the potential. But even if it doesn't lead to a complete overhaul of our current understanding, it's still providing a wealth of new information about the universe and raising some seriously thought-provoking questions.
All right, let's take a quick detour and talk about the tech behind this revolution. How is the ZTF able to spot these fleeting supernovae in real time? What's the secret sauce?
The ZTF is a different beast altogether. It's not like your typical telescope staring at a tiny patch of sky. It's got this massive, super sensitive camera that scans the entire northern sky every single night, looking for anything that changes in brightness.
So it's like a high-speed cosmic photographer snapping shots of these rare events as they happen.
Exactly. And the level of detail we're getting from the ZTF images is truly remarkable.
Now, I read somewhere that this data release from the DTF is just the tip of the iceberg. They've already published something like 21 studies based on this data, but there's so much more to come, right?
Oh, absolutely. This data is a gold mine for astronomers. There are countless more discoveries waiting to be unearthed in this data set. It's incredibly exciting.
Okay, so let's recap. We've got this incredible new data set from the ZTF that's making us rethink some of our most basic assumptions about the universe. We've talked about the potential challenges to the standard model of cosmology and some alternative theories like MOND. We've even touched on the amazing technology behind the ZTF and its ability to capture these supernovae as they happen. But there's one big question that's still looming in the background, and that's dark energy. What does this new data tell us about this mysterious force that's driving the accelerated expansion of the universe?
That's a fantastic question, and it's exactly where this deep dive is headed next. Stay tuned, and we're back. Still diving deep into the world of supernova and this whole expanding universe thing.
So before we took a little break, we were just getting to the good stuff, talking about dark energy. And I know everyone is dying to know, what does all this fancy new supernova data from the ZTF tell us about this mysterious force? You know, the one that's supposed to be accelerating the expansion of the universe.
Yeah, that's the big question everyone is asking these days, right? And the CTF data is giving us a whole new tool to try to figure it out.
So how exactly can looking at supernovae help us understand something like dark energy?
Okay, well, remember we were talking about how we use type Ia supernovae, these explosions, as standard candles to measure distances across space.
Right, because their brightness is supposed to be pretty consistent, so we can look at how bright they appear to us and use that to figure out how far away they are.
Exactly. Now, the cool thing is, if we measure the distances to a bunch of supernovae, like a really big sample of them, at different redshifts, we can actually see how the universe's expansion rate has changed over time.
Okay, I think I'm following you. So we can actually look back in time, so to speak, by observing supernovae that are farther away.
Exactly. And what astronomers have been seeing is that the universe's expansion isn't just happening, it's getting faster. The distant supernovae are dimmer than they should be if the universe was expanding at a constant rate. So something is pushing the universe apart, making it expand faster and faster, and that's something, well, we call it dark energy.
So the ZTF, because it's finding so many more of these supernovae, is giving us a clearer picture of this whole acceleration thing.
Precisely. Think of it like this. You're trying to measure the speed of a car, right? If you only have a few measurements, your result's going to be pretty rough. But if you have thousands of data points, well, you can get a much more accurate reading.
That makes sense. So more data equals more precision. So how is this new ZTF data changing what we know about dark energy?
Well, it's still early, but the ZTF data is giving us some interesting hints. First of all, it's helping us fine-tune our measurements of the universe's expansion rate, which is known as the Hubble constant. And the more accurate that measurement is, the better we can understand the properties of dark energy.
Okay, so we're getting a much clearer picture of how fast the universe is expanding. What else?
Well, remember that surprising thing we talked about earlier, how the ZTF data is suggesting that type Ia supernovae might not be as consistent as we thought, and their brightness might actually be affected by the galaxy they're in.
Yeah, that was a pretty big surprise.
Well, that finding actually has some pretty major implications for how we understand dark energy, too. If we're not accounting for those environmental factors directly, it could be throwing off our measurements of the expansion rate and therefore our understanding of dark energy.
So maybe we've been misinterpreting the data this whole time because we didn't fully get how these supernovae work.
It's a real possibility. And that's why the ZTF data is so important. It's making us double-check our assumptions and look for places where we might be making mistakes.
So what's next? How do we go about figuring out if our current ideas about dark energy need a major revision?
More data. And not just from the ZTF either. We need other telescopes around the world to study these supernovae in even more detail. The more information we can collect about these events, like their brightness, their spectra, and the environments they're in, the better.
And with all this new data, will we finally be able to crack the code of dark energy, solve the mystery once and for all?
It's really hard to say for sure. Dark energy is still one of the biggest mysteries in all of physics. It's this giant cosmic question mark hanging over everything. But the ZTF data is definitely giving us a new and powerful tool to try to solve it.
It's like we found a new piece of a giant cosmic jigsaw puzzle.
Exactly. And the more pieces we find, the closer we get to seeing the full picture.
But here's what I find exciting. Even if we don't solve the mystery of dark energy right away, the search for that answer leads to so many other amazing discoveries along the way. We're constantly learning more about the life and death of stars, how galaxies evolve, and the very nature of the universe itself.
Absolutely. It's an amazing journey of exploration and discovery. And with every new observation, every new piece of data we collect, our understanding of the universe just keeps growing.
Okay, so we've covered how the ZTF data is changing our understanding of dark energy and the need to be super precise in our measurements and to account for environmental factors. But now I want to talk about another interesting aspect of the ZTF data, what it means for alternative models of the universe, the ones that try to explain this whole accelerated expansion thing without even needing dark energy at all. Welcome back to the show. Right before the break, we were starting to talk about alternative cosmological models, the ones that try to explain the universe's expansion without needing dark energy at all.
Yeah. It's important to remember that dark energy is still just a hypothesis. It's not like we can see it or measure it directly. We're just inferring that it's out there based on how the universe seems to be accelerating.
So some scientists are searching for different explanations for this acceleration, something besides this mysterious dark energy.
Exactly. And there are actually some really interesting alternatives being explored. One that gets a lot of attention is modified Newtonian dynamics, or MOND for short.
Okay, MO, I've heard that name thrown around before. Remind me how MOND tries to explain things differently.
Basically, MOND suggests that maybe our understanding of gravity needs a little tweaking, especially when we're talking about really vast cosmic distances. It proposes that gravity might not weaken as quickly over those massive distances as we'd expect based on standard Newtonian physics, the stuff we learn in high school.
So instead of needing this dark energy to push everything apart, MOND is saying that maybe gravity itself just acts a little differently on a cosmic scale.
Right. And while it might sound a bit out there, MOND has actually done a pretty good job of explaining some weird observations about how galaxies rotate, things that don't really fit with our standard model of gravity.
Interesting. So where does this new ZTF data fit into all of this? How can it help us decide between sticking with dark energy or going with something like NOND?
Well, the ZTF is giving us this incredible level of precision in measuring how fast the universe is expanding and how matter is spread out. And we can take this precise data and use it to test the predictions made by both dark energy models and MOND.
So the ZTF data is like a referee in a cosmic boxing match between different theories of the universe.
Yeah, that's a great way to put it. And the more precise the data gets, the clearer the winner will be.
So we could be right on the edge of a huge shift in how we understand the universe.
It's definitely possible. Even if this new data ends up supporting the idea of dark energy, it's going to help us understand it way better. But if it ends up pointing towards something like MOND, well, that would completely revolutionize how we think about gravity.
Either way, it's a super exciting time to be following cosmology.
For sure. It's a golden age of discovery in astronomy, and the ZTF is just one of many amazing tools that are helping us push the boundaries of our knowledge.
Okay, before we wrap things up completely, I want to bring things back down to Earth for a second. Are there any practical applications for all this research? Why should people care about understanding dark energy, or MOND?
That's a great question. It's easy to get caught up in the heady stuff of cosmology and forget how it connects back to us here on Earth.
Totally. It can seem kind of abstract, so why should we care about something so distant and mysterious?
Well, for one thing, understanding the forces that govern the universe at the most fundamental level, like gravity, can lead to incredible technological advances that we can't even imagine right now.
It's like how exploring electricity and magnetism eventually led to all sorts of invention, like electric motors, computers, the internet, all kinds of stuff.
Exactly. We have no idea what amazing technologies we might unlock in the future if we can figure out dark energy or if we need to change how we think about gravity.
That's a pretty good reason to care.
And beyond that, trying to understand the universe is just such a fundamental part of being human. It speaks to our curiosity, our ingenuity, this deep desire to explore and make sense of the unknown.
So in a way, studying the universe is also about studying ourselves and figuring out where we fit into the grand scheme of things.
Exactly. It can be both incredibly humbling and incredibly inspiring.
That's a great point. So as we wrap up this deep dive into supernovae, dark energy, and alternative cosmological models, I want to leave our listeners with this thought. We've seen how this amazing data from the ZTF is challenging what we thought we knew and opening up all these new possibilities for understanding the universe. And this is really just the beginning. As more and more data comes in from the ZTF and other telescopes, we're going to keep making groundbreaking discoveries, and who knows what we'll find next. So stay curious, keep exploring, and never stop questioning the universe and our place in it.
Absolutely. The universe is filled with wonders and mysteries, and the journey to understand it is one of the greatest adventures we can possibly embark on.